All right. How are we doing this morning? Seems like it's the end of the semester. Try to have some fun with it. Talk about some fun next generation topics, bonus topics. Okay. All right. Well, first off, I guess we got people coming off. We can take another minute while we get prepped. Okay. I was just talking with my TA over the weekend in China. There was the there's a Beijing Marathon, and as of the last year, they started having robots running the Beijing Marathon. And last year they did pretty well, but one big problem with humanoid robots is they run out of battery really fast. I've talked about this before in lecture offhandedly. There's just a lot of power, so they will swap out. They're allowed to swap out the batteries for the robot running the marathon halfway through. Another big problem with these robots is that they overheat. Just like when we exert effort for our muscles, all that work goes somewhere. Some goes into mechanical work, moving us forward. Okay, some of which bleeds off into heat. That heat gets stuck in the body, heats up all your electronics. That's bad. It raises the resistance of your electronics, heats up your batteries. Within limits, that can be okay, but it really heats up the robot. So this year, you got to see a lot of teams. What they were doing is they would go up to the robot, take a bucket of dry ice, and go whoosh, and try to cool it down. But the big news was that a robot, seemingly out of nowhere, from this company that had not, to my knowledge, been developing humanoid robots, had a robot run a half marathon faster than the fastest human who ever did. Beat the human world record. Okay. Now the devil's in the details sometimes in how they accomplish this sort of thing, but it's kind of an interesting sweet spot because in a dead sprint right now, humans would still beat a running robot. In a marathon, a full marathon, a good running human could still beat a robot, but the half marathon might be the sweet spot for right now. I think it might be the first world running record that's been beaten by any humanoid robot. So, big deal. It's a big deal. What do they use? Well, we don't know for sure. We're trying to figure that out. Me and my TA, we're trying to talk about the methods that they're using. But they more or less use something called deep reinforcement learning. Something that's covered a bit more in my other class. Okay. On machine learning, but in principle, it's optimal control. Okay. But there's some cost function, some reward function, okay, that they want to optimize for the robot running fast while not falling over. Anyway, just telling a story about a really fast running robot while people trickle in for the last in-person lecture of the year, okay, for this class. Thanks all for coming, okay? We're gonna cover some fun bonus topics today, which I think will hopefully give you all some nuance for how optimal control can become tricky in practice for certain kinds of systems. But we'll get to that in a minute. So on Thursday, we will have a project workshop, okay? So I recommend coming in with your project groups on Thursday, again, in person, okay? Unlike normal Thursdays, we're actually gonna be in person, and you have all submitted your drafts, your project drafts, so we can look at them, and you get to meet with the TAs, and they're gonna try to guide you on how to finish up your project, again, due on the last day of finals week. Okay, make sure you get your report together, and make sure that you get your presentation together. Again, less than a 5-minute presentation. You upload it to some kind of YouTube link. Can be uplisted. It can be unlisted if you want, so that way it's not publicly available. However you get it to us, just give us a link to a video of you giving your presentation, and that's never been easier to do. Back in my day in grad school, that would have been a lot more effort to put together a video presentation. Here, just give a presentation you can just use Zoom and use the Zoom record feature, okay, of you giving your presentation. And the goal of the presentation is just to talk about your whole project from start to finish. Hi, I'm this person. This is my team. And everyone talks about what their problem is, how they tried to solve it, and what their solution was. How did it work? Okay? That's what we need from you. for the project presentation. Okay? So make sure we're doing well here. Yep, we're doing well. Great. So, awesome. So let's just write this out. All right. So today, 2026-04-21. So we're going to have a project workshop on Thursday. It's in person. Okay, here in AME 106, okay? Be here with your project groups to talk about your project, okay? And that's your last obligation for the class, is your project. We're done with homeworks, we're done with quizzes. Okay. All right. So we're in the home stretch, which means that the stuff I'm telling you today won't be on any homework, okay? Won't be on any quiz, but it should be fun, okay? That's the goal. Or at least maybe hopefully get you to think in a different way about optimal control. So far in optimal control, we talked about systems that move in continuous time, where we would have some x of t, where this is your state vector. And they move as some function of the state and some control input. Okay? So let's say just where x of t is some continuous function, meaning it just moves through space smoothly. There's our state is moving continuously and not discretely. So this is for continuous dynamics. We'll often draw over time. Oh, here's some state over time. It's the position of my little pen holder right here, moving it over time. And we draw it as some smooth curve, some differentiable curve even, okay? What you do not see are sudden jumps. Whoop, right? You don't see that because, look, we're defining its derivative, okay? We define its derivative. If we're defining its derivative, that means the state itself is going to be it's going to be continuous because, yes, you could suddenly change your derivative really quickly. And that'll create a cusp, as we learned from Calculus 1. But it doesn't create a jump, okay? But what might create a jump physically? Anyone can think of an example for just a physical system, something I can do with this. If I'm looking at the states of this system, what are the states of this system? Let's just say up and down. Anybody? Up and down, physical system. This little folder here. What are the states? How many states? Just let's assume we're moving up and down. How many states? Did I hear that? Two. Position and velocity, right? Okay. Oh, it's moving around. Look at this nice continuous position, continuous velocity, right? Okay. What happens when it hits my hand? Say that again. Stops or bounces. I agree. So let's look at if one of my states is my velocity, we'll call it v of t, right? It's going to look like this. Woo, boing. Okay. So you have an impact. Sorry. We have an impact. Sorry, let me just make sure. I'll redraw this because it's going down. Okay. So we have, there's our y-axis or x-axis. So it goes down. It's decelerating. It's accelerating downward, right? Then it comes to a stop. Let's write this. I'm gonna make it in red so you can see it. Right. There you have an impact. It has made contact. That's a state. It's jumped. Okay? So that's, and this happens in all kinds of systems, right? Things that maybe, so things that we might want to do things with control. And again, we've done some examples of robotic arms, right? Imagine our robotic arm comes up and, tries to high five another robotic arm, right? That's an impact. And that's not quite captured, my friend. The problem is using your pen holder as an appliance. You can't use your pen holder as a pen holder. Okay, all right. You can't capture that in this continuous set of dynamics here, can you? Because all of a sudden there's a big change in one of your states. Instantaneous, unless you make this like infinite, which I guess you can kind of try to do, right? So what you have are these events. You have an impact event, okay, where you have some continuous dynamics where x dot is equal to some f of x and u. Forgive the of t being dropped. You have your continuous dynamics. Okay. Then after then you have an impact. Okay, you have where you take your state before the impact, the state after impact, we'll call it plus, is equal to some function of your state before the impact. This is an instantaneous. This is an event. These are discrete dynamics. This is discrete mapping. Okay, meaning you have some state before. This is our state after. Okay, and then it might go back to some set of continuous dynamics again. Right? If this is a bounce, it's now back in the air again. Now it's under this continuous dynamics of being flying through the air, right? Until it impacts again, right? That there is an impact event. Okay. So if you take biorobotic locomotion, which I believe is being offered in the fall, they care a lot about these impact events. Why? Because if you're talking about this biorobotic locomotion class, a lot of robotic locomotion is legs. And what are legs doing to the ground? Impacting over and over and over and over again. So one example that you will code up, if the class is anything like it was taught by Dr. Clark in the past, is that you would have some position of some ball. We'll call that position of that ball z of t in the air. Okay? Z of t, and this is time, bounces like a ball, okay? And here are these impact events. Okay? Now, for that ball, this ball falling through the air is exactly like my pen holder. It has two states, right? And you would see your z of t and your z dot of t, which is your second state, your velocity, right? It goes from, let's say that's, this is 0 up here. It goes to, let's see. Or that's, I guess, yeah, that's 0 velocity. Right? It has all these little jumps. There's an impact event. There's the impact event. Jumps up there, jumps up there, jumps up there, right? Okay? So if you are modeling a system that has impacts, it's not enough just to say, hey, x dot is equal to f of x and u. All right? And this creates all kinds of interesting challenges for control. Okay? All right? And one of the ways that people, when they're controlling some kind of system that's going to go through impact, let's say it's an arm going to pick up this pen, and you don't want to smack the pen, all right? You'll often have a constraint on your controller saying, by the time you touch this pen, I love the shirt. Do you mind standing up? I want to see the shirt proportions, make sure it came out right. Yeah, pretty close. Yeah, this is good. Thank you. All right. Okay, cool. Awesome. So one constraint that you can do is you have a robot arm picking up this pen is you say, by the time you get to this pen, I want 0 velocity. I want it to coast to a stop. Then there's no impact force, right? Then you say, okay, you just say, hey, come to a stop there. Now grip slowly. Now move again. There's no, then at which point there's no sudden jump in the impact, okay? Sometimes people will call this a jump map, meaning that it takes the state before, the state right as I'm about to hit the pen, and then the state will jump to some other state after the impact, right? If I force my system to come to a stop right before I do anything, there will be no jump. Everything's cool. Everything's chill. All right? There's no jump in the state. Gesundheit. Okay? There's a term for these systems that have both continuous dynamics and these jumps, these hybrid jumps. They're called hybrid dynamical systems. Okay. Continuous dynamical systems that also have jumps in state space are called hybrid dynamical systems. Yeah. They're hybrid. They're continuous and they're discrete, both things together. Hybrid is one of the most overused terms in, I think, all of engineering, but because you can take anything and anything else and you say, I put them together, it's a hybrid. All right? Yeah. But this is a common mathematical formulation called the hybrid dynamical system. Okay? Common applications are manipulation, which is hands. The man in manipulation stands for like hands. Okay? So I'm making and breaking contact with all my fingers on this pen. Manipulation. Okay? Also things like legged systems. Okay, that's my specialty. A lot of the great mathematical work done for controlling legged systems is in the domain of hybrid dynamical systems because you have the impacts of legs hitting the ground over and over again. Okay? And it's not just that, but any kind of switched system. So even if you are, let's say you have an autonomous car, you might have one controller that's for driving, maybe another controller that's for evading an accident, right? There might be some internal state of the controller that will jump, okay? And you can treat that as a hybrid dynamical system. And the idea is that you have some event that triggers a jump, and it's called a guard. Okay? So the guard for this case of dropping this being my hand, okay? The guard is when the position crosses this threshold. Triggers the impact, hybrid dynamical system. Okay? All right. So the question then becomes for all of you who are in an optimal controls class, how does this affect optimal control? Well, naturally, we no longer can just count on the fact that we have this x dot is equal to f of xu governing everything. So what do we do? For instance, how does this affect trajectory optimization? How does this affect, particularly trajectory optimization? That's an interesting one. But before we get to that, let's just recall how we would even model. Model changes in contact. Okay. We go back to our Euler-Lagrange equations. And particularly in manipulator form. Okay. That is our m of q double dot, where the q is your generalized coordinates, okay, plus c of q dot, that's your Coriolis vector, plus g of q is equal to some external forces that you're adding, some bu. But then we added some term called J transpose lambda. This is called your contact Jacobian, okay? All of this stuff is all the stuff we did when we went through our coding tutorials on how to do Lagrangian mechanics, which we then turned into a simulation of a two-link robotic arm, which we then turned into an inverse dynamics controller that used this equation, which then we turned into an operational space controller that controlled exactly the way it moves through space. We did all this ourselves in class, all immortalized on the servers of YouTube, okay? One thing we didn't add was this. Okay, well, the J is the contact Jacobian, and the lambdas are your Lagrange multipliers. We talked about this very briefly. Okay, these are Lagrange multipliers, M-U-L-T, period, multipliers. Okay. And these Lagrange multipliers we talked about in the past, those are your constraint forces. That's the thing that's preventing my pen holder from going through my hand when I'm holding it like this, right? So if you have some constraint, so you have some what we call the holonomic constraint. Okay. Where you would say, hey, I have some function g of q, which is equal to 0. So if I am on the ground and I'm in contact, okay, if I'm in this contact mode where I'm touching one to the other, okay, I would create a function that says the vertical position of this pen holder minus the position of my hand equals 0. It's constrained to be on the ground. That's what g of q would be. So this would be must be true in contact. Okay? And when you're solving these equations here, you will, if you're doing your forward dynamics, you're going to say, hey, here's all the torques I'm applying. What are my accelerations? And you will also solve for your Lagrange multiplier. The Lagrange multipliers are your constraint forces. Your constraint. Okay? That makes this the normal force, keeping it from going through the ground, right? If I push harder on it, the normal force will push back harder. And that, my friends, is that lambda. Okay? Every constraint is going to have one lambda. That's your constraint force. Now, there are rules for contact. My friends, there are rules for contact, assuming my hand is pushing this up. It's holding that pen holder up, going to the ground. What if I try to pick up this pen holder? Is this force going to suck it back down to the ground and hold it there? No, unless it's a suction cup, which we're not dealing with today. Okay? The force can only go one way. The ground can only push up. It can't suck me down unless I got Velcro shoes. Right? Okay? We call the fact that contact forces go in one direction. They push and don't pull. In what we call unilateral contact. Okay? So people will talk about unilateral contact models. What they mean is the ground pushes, it doesn't pull. That's what it means. Okay? So if you are making a computer simulation and you're coming up with all these equations of motion, and you're saying, okay, this pen holder, I love that's rubber, it hurts me less. Okay, right? This pen holder, flying through the air. Check and see if it hits a guard. It hit a guard, there, hit a guard, right? What happens? There's an impact that changes the state. It changes the state, and now it's in contact, okay? How long is it in contact for? Well, it's in contact so long as that doesn't go negative. If that goes negative, it means that the constraint force is going to try to pull it down. So what happens? It separates. So in contact, in contact, in contact, all of a sudden it's negative. It's out of my hands. Turn off the constraint. Until it hits my hand again, turn it back on. Okay? So if you're simulating a system that has contact, what you want to do is you want to set up all the guards, all the things that this could contact. Contact my hand. Check that. All right? It can contact the floor. I regret that. Okay, come back. All right. You can check that. If the guard hits 0, change your equations of motion. You add on this term. Okay? And you keep assimilating now using these new equations and now have this term until that goes negative. It breaks contact. So on and so forth. Okay? So this is handy for like an example. Let's say you got a walking robot. You could have your, look at this fancy walking robot. Okay, I'm better at drawing robots than this. Hope it's evident. This is my design in case you're curious. All right. Proceeds benefit charity. Anyway. Okay, there's your walking robot. It's floating in the air. Okay? Now we could compute using Lagrangian mechanics. People see that? It's like a robot with 2 legs in a weird walking way. Look at that. Yeah. Okay. Right? Let's have it float in the air. So we can set up the Lagrangian mechanics where we could say, hey, this is our base link. Okay, this is where we start with. Okay, and then we add on the energies for each of these other pendulums that are attached to it, just like we did with the double pendulum. Let's add more pendulums. Okay, you can create this as a floating base. All that means that you have generalized coordinates for x and y, that those are generalized coordinates as well. They're degrees of freedom of the system, just like when this is in the air. You'd have generalized coordinates for all the positions and all the angles of this is in the air. You do the same thing, but now attach little legs to it. You could set up your Lagrangian mechanics that way. Okay? Now, when a foot touches the ground, you're in contact. Okay? All of a sudden, you take those same equations, but you add in some J transpose lambda into them. There's your contact Jacobian. Thanks, folks. Okay, there's a contact Jacobian. If this other leg hits the ground over there, you add another contact Jacobian. Actually, you add more rows to your contact Jacobian. Okay? Because you have more conditions of contact. You would write them as, where is it? I'm sorry. Here. You just create your function. These are all the things that must be true when you're in contact. Here's another example. Here is a mass on a hill. Okay? Let's assume that there's some angle alpha there. Okay? What must be true for the mass to be in contact? I'm so bad at writing today. What must be true? Let's say we have some x coordinate and some y coordinate. Those are our generalized coordinates for our mass. What has to be true? Well, it's just a little bit of trigonometry to say that this mass has to be on that line. Okay? That x of t is going to be some, we'll just say some distance d up from that is going to be what? Minus d cosine of theta, of alpha, sorry. And that y of t, and d will change over time to be clear, is going to be equal to d positive d sine of alpha. Okay? All right? And what we could do is we could solve, we can try to get rid of d. We could try to say that d is equal to y of t over sine of alpha. Okay, therefore x of t is going to be equal to, when we substitute it into minus d, it's going to be minus y of t over sine of alpha times cosine of alpha. That's a cotangent. Let's put it on the other side. And this is going to, if you solve all this, is going to be equal to the tangent of alpha is going to be equal to minus y of t x of t. So if we're going to make some function g of q of t, that has to equal 0. It's going to be that tangent of alpha plus y of t over x of t equals 0. Okay. This is just trig. Okay. Where our coordinates are x of t and y of t. And our Jacobian, J, is going to be partial G, partial Q. All right? So we compute that. Jacobian is going to be a 1 by 2. It's going to be partial G, partial Q1, which is x, and then partial G, partial, which is y. Just giving you an example of how you start to apply the contact Jacobians. We set up a condition for contact that the mass has to be on the ground. We set up some function. We then try to solve that function. Doing it real quick on the fly. This is more math than I hope to get in today. I'm sorry. It's the last week, the last day of in-person class. And then, of course, we have the project workshop in person on Thursday, as I talked about. Okay. All right. But that's how you start setting up your contact Jacobians. Okay? What it means is that whenever you make or break contact something changes in your dynamics. Okay? So imagine you're doing some optical control. Let's say you're doing trajectory optimization, right? You have a robot arm. Sorry for all the robot arm examples. I am going to go, my task is I'm going to try to grab this object and take it back to where I started. So that means I have one set of dynamics with no contact. Then I grab, now I have a new set of dynamics that are in contact with this and take it back. Okay? My dynamics changed. Okay? So how do you do a trajectory optimization where the dynamics have now changed? Okay? Well, it's actually pretty intuitive. What you do is you say you have one trajectory optimization that you run for one set of dynamics, and you say, I'm going to end at this state. Then you do a second trajectory optimization, saying, I'm going to start with this new state, now with new dynamics. And go back here. You just do two different trajectory optimizations. As long as you know one of them is going to start with no contact, the second one's going to have contact, you're golden. Okay. For trajectory optimization, with contact. Okay? So what you do is you run multiple trajectory optimizations with different dynamics if you know the order of contact. It's that simple. Okay? If you know the order of contact. In this example I gave, I'm going to start with no contact, then I'm going to have contact until I finish, right? I know that order of contact. This method is called mode scheduling. Okay? Imagine you have all kinds of projects that you're working on for your class, one of which I think is like a submarine. Someone's working on like a submarine model. Are you okay? Sorry, I heard it was a snatch. Okay, good. I heard a snatch. I heard like an aggressive snatch of the attendance sheet. Okay. Right. So imagine the submarine's going to go and pick up something from the floor of the ocean floor and pick it up and take it somewhere else, right? You know the order of what you want to do. You are submarine, not making contact with the thing. Then you make contact with the thing and take it back to the surface, right? You can mode schedule. You know one, then the other is going to happen. Okay? If you know that, it's just as simple as running two trajectory optimizations. No big deal. We've known this in all kinds of applications. Again, legged locomotion is the example I like to use the most. Okay? Right? So if I am walking, I literally know it's going to be left foot, right foot, right foot, right foot, left foot, right foot, etc. I know that fact. So running a trajectory optimization that gets me from there to there, I just string together 1, 2, 3, 4, 5, 6, 7 trajectory optimizations. Okay? A lot of those are redundant. You kind of already know how to get from one point to the other, right? Okay? But one thing that doesn't do, what if I do this? What if I want to skip? Well, I'd have to tell it, you better skip. Honestly, I forget the context sequence. Skip. I don't remember how to skip. I just do it, right? Okay? Skipping is a different sequence of contacts, a different mode schedule. So I would have to tell it, you're skipping or running. Running is generally understood as being in the air, one foot then the other foot, right? I'd have to make that choice beforehand. But what if I don't know which one is the right one to do? Like, imagine I'm having a task, like, I want to get to that door, okay? And I say, hey, I have 20 seconds to get to that door. What am I probably going to do? Probably going to want to walk, right? Okay? That's one set of contact sequences. If I say I have 5 seconds to get to that door, I'm probably running, right? That's just one number I would change to my trajectory optimization, but the solution would run. At least you want it to run. It might be impossible to walk fast enough to get there in 5 seconds. I'm not a power walker. Okay? So if you don't know for sure, or don't know at all, the contact sequence, you can't do mode scheduling. I guess you could try. You could try saying, try walking, run a trajectory optimization, see if that's good. Try running, see if try the trajectory optimization, see if that's good. But what if I want to walk for part of it, run for another part of it? Or skip for part of it, hop for a part of it? The number of combinations you have are crazy. They just expand like crazy. They grow exponentially, okay? Even just think about it as, from a simple standpoint of just, if I'm going to move this from one point to another, right? I'm assuming right now that I have this in my hand and I keep it in my hand over here. That's the task. Move this to there, right? There's nothing stopping me from going that. Different contact sequence, different mode sequence. That's a silly one. But you know it's also a really complicated mode sequence? Gripping. Which finger hits first? Doesn't matter. But I want a mode schedule. Which finger hits? And when I drop it, which ones release? Where do I put them? Okay? It becomes a complicated problem. So people invented this really interesting approach to optimizing a contact sequence without mode scheduling. Okay? Where am I losing my pen? Okay? To optimize a trajectory without a known sequence of contacts you can treat contact as a more flexible optimization constraint called a complementarity constraint. You're all experts at setting up constraints. You had to do a lot of that for your trajectory optimization homework. Okay? The idea of a complementarity constraint, what's often called a linear complementarity constraint. Let's say you have two values. We'll call it A and B. Multiply them together, they got to be equal 0. What does that mean? If A isn't 0, what does B have to be? 0. If B isn't 0, what does A have to be? 0. One of them's got to be 0. They can both be 0, but at least one of them's got to be 0. Okay? That's a complementarity constraint. They have to be complements of each other, not complement like you look lovely today. One has to sort of be a pair of the other. If one's not 0, the other has to be 0. Okay? Well, how does this, and this is a constraint that we could write, that's an equality constraint. We could write that in an optimization, right? We write equality constraints all the time. We did it for our homeworks. Okay? How can we apply this to contact? Well, I have two quantities here in this complementarity constraint. At all times, one of them must be 0. Okay? Now I'm going to have my little example pen holder again. Let's assume for a moment I'm not holding it. It's just floating in the air right now. Okay? And I want you to think about two quantities. All right? One is the distance between the pen holder and my hand. Okay? The distance, right? The other of which is the force between the pen holder and the hand. Okay? It's in the air. Is the distance equal to 0? No. Is the force between them equal to 0? Yes. I'm holding it up with this other hand. Ignore it. Okay? One of them is 0. Now, it's on my hand, pushing it in. Is the distance between them 0? Yes. Is the force between them 0? No. You can treat contact like a complementarity constraint. And what are these two quantities? One is the distance between. Let's take a little block. Some block there. And there's some surface you can make contact with there. Let's have two quantities, one of which is the contact force between these, the lambda, the contact force. And the other of which is the distance between these two things. We'll call it phi, just because that's what it's called in the paper that really popularized this technique for specifically trajectory optimization, posted 2014 in the International Journal of Robotics Research. Okay? It's not the first to posit treating contact as a complementarity constraint, but it is the first to show you can use it as an optimal control method. Okay? So the idea is that here, your lambda, they are decision variables, my friends, in your optimization problem. Okay? And they are subject to the constraint that phi times lambda equals 0. So for every set of contact points that you have, set of that condition. The optimization can change the contact force, but if it's going to do that, guess what it's going to have to do? It's going to have to drive that distance to 0. If it wants to lift that thing away from it, it's got to make the contact force 0 again. Okay? Pretty clever. And the beautiful thing is you can also say, you know, we talked about how the unilateral force constraint that we have, that we can only push with the ground but not pull. Okay? Well, we can add that easily. You can say lambda must be greater than equal to 0. That's a unilateral contact force. Okay? Constraint. Okay? So what that means is that for your trajectory optimization, at every node of your trajectory optimization, you're deciding, hey, what is my contact force? And the optimization can say, oh, it's either 0 or some non-zero value, whatever helps, right? And if it's non-zero, it better be not touching. If the contact force is non-zero, they better be touching. If you want to separate them, the contact force must be 0. What the complementarity constraint does. Pretty clever. Okay? There's other nuances you can add too. You can also add friction constraints. You can add static friction constraints using the same thing. If you have a contact force that is in two different directions, you have a friction contact force and a vertical contact force. You can say that in order to stay in static friction, one's got to be the one they're bounded by static friction. Okay, like if we know that mu vertical, we'll call it mu normal, the mu static friction times lambda normal, okay, it's got to be greater than or equal to the absolute value of the friction force, right? There's a friction constraint. You can add those constraints. Okay. And this was really handy, actually, for a very particular project that Michael Posa, the first author on this paper, worked on. He's now at University of Pennsylvania as a professor there, where he works on a lot of contact-related robotics. How do you pick up and drop off things? And he uses these, and he's advanced a lot of the state of how these algorithms work with these complementarity constraints in the years since. Okay? But he was working on a project. It was this weird and awesome and wacky running robot that he was working with. Okay? And where this robot it was built in a way that was inspired by an ostrich, in that it had all kinds of wacky spring mechanisms that, like, basically what you would do is you would take the leg, and if you shook it, it had all these linkages where the robot would go, it would just kind of actually move itself in like a leg in this motion, right? And there are all these little hard stops where it would clack into a thing, clack into another thing, clack into another thing, clack into another thing, making and breaking contact all over the place. They didn't know it was a good contact sequence for these mechanisms. So they invented this method to do trajectory optimization, okay, for the robot. All right. Let's see, maybe I can find it. If I just pull up this robot here. Let me see if I can find this video. What's up? Yeah. Go. Go. This is it's between two plates right here. So it doesn't balance. It didn't balance yet in 3 dimensions, but this kind of wacky mechanism where things are clacking into it left and right, and it's running on this treadmill super fast. Okay. And the beauty of it is that, like, if you found the right way to try to push energy in the system with its motors, it would self-stabilize and keep running. And it's this crazy mechanism. Look at this. Yeah. Anyway. So this trajectory optimization was built in part to help make this robot run faster. Okay. This is a number of years back. Well, yeah. They later did bigger versions of this robot, but you can check it out. It's called the Fast Runner, and it's built actually, it's by a laboratory out that direction west. Sure, that direction's west. West out in Pensacola, called the Institute for Human Machine Cognition. Okay, it's out in Pensacola. They do a lot of work. And that's not just robotics work, but they also do like human genome research. They do all kinds of cool, nifty things. So let's see here. Yeah. This is powered. This is powered. So this is a physical machine, right? So what they would do is they would create a computer simulation, just like we did, using Lagrangian mechanics. Okay? Say, here's our equations of motion. Keep asking questions. This is good. All right? And then say, okay, here's our dynamics. Set up the equations of motion. I don't know if this particular result uses the linear complementarity constraint method. Okay? But then once you know the torques you want to put in over time, it was just like this sequence of motions, right? They would actually take the motor, and they would say, they'd say, apply this much torque now, then this much torque, then this much torque, this much torque. That is, my friends, what'll come out. Same thing that happened in your homeworks, right? Here's your U of t, and that U of t would happen to be torques on the motor, right? You have these different points and say, apply this at time whatever. That's what they do. Other questions? All right. Okay. So now let's see if we can pull this up again. When it comes to when it comes to trajectory optimization, okay, this is one of the ways that people found a way to get around the challenges of different contact sequences. It was helpful for these robots. People also used it for a long time for, figuring out how to grip objects with fingers. Fingers are making and breaking contact with things all the time. Where do I grip it? How long do I grip it? How do I release it, right? That kind of thing. All right? So, and one thing I want to leave sort of as we finish up here, okay? Sort of like the newest stuff, okay? Okay. I mean, like everything that we're talking about in class, all right, has direct influences on a lot of the latest and greatest control methods, robotics and beyond. Okay, I use robotics as an example a lot of the time, but like when it comes to model predictive control that we covered, right? Model predictive control was used in power plants first, in chemical mixing plants first. Okay, when it comes to also trajectory optimization methods are used heavily in understanding how people move in biomechanics. Okay, people will create computer simulations of full-on skeletons of people with all the muscles and tendons, and they'll say, okay, if I assume a person cares about not using a lot of energy, not accelerating their muscles too much, but having to accomplish a task, does it move like a person, right? And they will use it to try to figure out, like, hey, this trajectory optimization says that if I give it this cost function, it walks like a person. That suggests that cost function might be what we care about when we're walking. And why is that useful? Because then we can have the idea is we would then have a prediction as to how that person would walk if something happened to them. Let's say they had a lower leg prosthetic device. How would they walk with it? Well, one thing you could do is you could build it and give it to a person and see how they walk with it, at which point you have to get a patient trial and all these things. Or you could ask this computer simulation with a trajectory optimization. This is how it walks. Great. Maybe we can make the prosthetic different so it walks different, right? Okay. So in the field of biomechanics, trajectory optimization has a different name. They call it predictive simulation. They don't use it to control a robot. They don't use it to control a power plant. They use it to control a submarine. Okay? They just want to predict how people move. Okay? But even some really cool stuff. Let me see if I can pull up this. Mute. Now, with the caveat that I don't know for sure if this is what they're doing. Okay, fast-running robot. Let's see. Okay. There you go. This happened this weekend in Beijing. I was talking about it right at the beginning of lecture. This is a robot running a half marathon, okay? Faster than any human ever ran a half marathon. This is a big deal. I'm pretty up on my humanoid records. I think this is the first time a robot beat any running record of a human. No robot has beat the 100-meter dash of a human or a full marathon or a 400-meter dash, at least to my very recent knowledge. But here we go. Yeah, and this happened in Beijing. And by the way, as far as I know, a company that had not been publicly building robots before. This is Huawei. They build like internet communications devices. And now people will just like, oh, I'm just going to hire a bunch of robotics engineers. We're going to make a robot in secret, make it run a half marathon. Crazy. So there's absolutely optimal control methods on board this, but they use a very particular method. Pull this up. Okay. Called reinforcement learning, or deep reinforcement learning. and it has so many direct parallels. In fact, it's considered an optimal control method. Okay, we talk about it a bit in my other class. We covered it, which is all up on YouTube if you ever want to watch it. We cover deep reinforcement learning, but at its core, what they have is a simulation. With some small caveat, I don't know 100% for sure if this is what they did with their robot, but looking at it, squinting, I think they used deep reinforcement learning to control this robot. You have a simulation of your system, which we know how to do. You're all Lagrangian mechanics experts. You're all Lagrangians now. Who among us is not a Lagrangian? Okay? You have a simulation of your system. Okay? Then you have a controller that's parameterized by decision variables. Okay? One of the first things we talked about was what is an optimization? Well, what are the things you need to know? You need to know the decision variables, right? Okay? And they define a cost function, but they call it something different. Call it a reward function. Now, what are the constraints? As far as I can tell, they don't have any explicit constraints. They just have a reward function. They have to be very careful how they make their reward function, because they want the reward function not just to be move forward, because then it might, just fall on its face and flop on its face. I actually published a study as a silly little study that I love, where I literally took a very simple computer simulation model of a robot and said, okay, what's the least amount of stuff you can tell it to do? And it does something that looks like normal locomotion. Okay? You tell it to go forward, it flops on its face. Okay? And things like that. So I tried to come up with the minimum number of constraints that you need to get it to walk to get it to move in an interesting way. But this all that needs to be put into a reward function, because deep reinforcement learning, generally speaking, doesn't have constraints. So it means they had to tell the robot to maybe go forward longer. Okay? Go forward so long that you can't just flop on your face, because then you won't go further anymore, right? Okay? So you have to encode all of that in a reward function, which is like the negative of a cost function. -1 times cost, right? So if you're getting good at setting up cost functions in your trajectory optimization problems, well, guess what? That skill is directly transferable to this reinforcement learning approach that's becoming super common. But again, what do you need? Simulation. You need a controller parameterized by decision variables. Now, their controller is parameterized in a weird way. They're all just parameters in a neural network. Okay? So basically, instead of it being a spline curve like we've done in the class where we have those little splines, right? They are values in what we call a neural network. Looks like this, where here are your inputs. Those are your outputs. I'm sorry, I'm just being a little sloppy right now as we finish. And these connections here are decided by your weights, your decision variables. They're called W's, right? And there are biases, blah, blah, blah. That's a deeper question than we have for today. So, but all of these things that we're talking about, they continue to apply even though the techniques continue to change, right? That's all I got for you today, right? Got to watch some videos? We had a good time? Question? Yes? So the question is, how much time we got here? You're all dismissed, but if you want to learn anything about neural nets, okay, you can stick around for 10 minutes, okay? So the question is, how do those decision variables affect the torque output? And I won't be offended if you have to go. All right. You had a great semester. You all been great. I really appreciate you've had a great semester. This has been fun. So thank you so much for coming. I just want to say that. And good luck with your projects. A neural network, the idea is that you have some input, then it goes into some function we call an activation function. It often looks like that, like S-shaped, or it's like, elbow-shaped. And the idea is that it could be something like a hyperbolic tangent of your input x. So let's say our input is x, our output is y, right? So your weight, your W, for instance, is going to be along that line. We'll call it W1. It's going to multiply by your input. Okay. Now that doesn't do a whole lot. All that will do is if you did your hyperbolic tangent, if your hyperbolic tangent is 1, here's x, here's y. If your weight gets bigger, it just sharpens this, right? How it would work. Okay. But if you add more of these activation functions, think of them as neurons, just like neurons in your brain. You have an input. If the input is low enough, it doesn't fire. If it's big enough, it does fire. Okay? That's all a neuron is to a neural network. Sorry, biologists, there's so much more to neurons than that. So the way that they talk about it in artificial neural networks is that's just a function that turns on when a number gets bigger. Okay? And you just modulate how it turns on with these numbers. And it's a neural network because we will have 1, 2, 3, 4, where this is your input, this is your output. Here's all of your tanh-h's, your hyperbolic tangents that just look like something that's off and then it's on when x is big enough, right? And then you multiply the output or by W1, by W2, W3. You have more parameters. What happens? You can start making different shapes. Okay? That shape, what's your input, what's your output? Now, this is actually not a very good neural network. Okay? The way that we get good neural networks is by having not just one into the other, into the other, to the other. We have an entire layer of neurons where they all feed into here. These all feed into here. And each of these little wires has a different W. Okay? There's your input. There's your output. Sometimes that's not enough. Give you all the shapes that you might want to have. Here's your input. Here's a layer. Here's another layer. They're all connected there. Each of these activate and then go to there. All these combinations there. All these combinations there. You get all the combinations, right? It's like a little web of connections, right? Okay? Then all of these come back to some output here. Every single one of these lines is a W that multiplies the input and output. Here's the beautiful thing about a neural network. In essence, if you have a big enough network with enough connections, particularly in these middle layers, you can have that approximate any functional shape, which is crazy. And the nice thing is that it applies to more than just one input and one output. You could have multiple inputs, multiple outputs. Okay? You could see how the number of W's, they're called weights, starts to blow up, right? Let's say there are 6 here, there's 6 here. That means there are 36 connections between them, 36 weights. A lot of decision variables, right? All heard of ChatGPT? Got billions of these in its neural network. It's a big neural network with an interesting structure. You can play with the structure of these so it does cool things, right? And in the way that you optimize those weights, these W's, is you train it, okay? What do you mean by train? It just means optimization. It tries to come up with an optimization that optimizes the performance of the system. Literally, it's an optimization. You have a cost function. You have decision variables. What are they? They're your weights. Technically, there's also something called a bias that you add as well. It's very important, which is just saying that that you take your input and then you multiply it by some W, but then add a bias to it as well, physical offset. So over the last couple decades, we figured out how to do gradient descent to optimize all those weights pretty well, especially when you have GPUs, graphics processing units, to help parallelize the process, okay? We learned a lot of tricks over the years. And so the controller, for the purposes of you, here you have your big neural network that we've just trained using a computer simulation, blah, blah, blah. Don't have a ton of time to talk about it. But in goes your current state of the robot. Current state of your system. What comes out? All your control inputs. That's your controller. Okay. Answer your question? A little bit? Yes. Yes. Yeah. Yeah. So in the example in machine learning, we did a cart poll. Yes. And it was really just push left, push right, right? Here, thanks, Christian. Thanks for coming. All right. Here's this continuous value for the torque. That can come out as well. I know you're in the course. I'm just giving this for everybody. Okay. All right. Thank you all so much. I appreciate it for coming. Hope you learned a couple things. Take care.